All right, hi DiffyQs, how are you? If this is your assignment for, oh my goodness, I'm losing my days, for Thursday, I guess is what the day is, right? Yeah, so the day that this is posted on the same day where I ask you to review your notes and just look over things, okay? So in this screencast, we are going to just kind of bring us all back to where we left off and then give you a problem set that I'll draw from your text. And if you see here, it's what the heck? I copied it right here, but this is just from the chapter 2 review page. But let's focus on this stuff first, okay? So I want to focus on, just in a nutshell, the 3 novel ways we solved DiffyQs before we left for break. The first one was given a differential equation in what's called standard form, first order linear, right here, okay? And when we had DiffyQs in this form, we had an integrating factor, and that integrating factor was e raised to the indefinite integral of p of x dx. And you may recall what we did was we multiplied the entire DiffyQ by I of x, by this integrating factor, which then yields a differential equation that we can integrate to solve. So let's do an example of method number 1 together right here. Okay, let's just review that. I wrote this question down here. Okay, so here we have a differential equation, and when we look at this DiffyQ, it is absolutely in the simplest form of a differential equation, which is first order linear. Okay, and you'll notice here it does say x y prime, and if that bothers you, you can certainly go ahead and rewrite this as x dy dx plus 1 plus x times y equals e to the negative x sine of 2x. Okay, now we have to make one modification before we begin. For this to be in this nice standard form, we want to make sure that we are multiple competing thoughts here. We're going to divide this differential equation by x so that my first term here is just dy dx. Okay, and when I do that, I get this. And it's really interesting, but you know, this right hand term, right, this right here, this f of x may look intimidating. And while it may look intimidating, it is absolutely still in this form. I mean, what's left over here is just a function of x. So we are heading in the right place. Okay, so then here's what happens. P of x is this right here. And I need to figure out what the integrating factor is. The integrating factor is going to be e raised to the indefinite integral of 1 plus x over x dx. When I'm integrating 1 plus x over x dx, it's going to behoove me to rewrite the integrand like this, right? So kind of blowing the dust off of our integration brain. And then when I integrate, I get this. Everyone good? All right. Now it's going to behoove me to manipulate this as well, because who wants to deal with that? E to the power, where the power is added. Let's write it like this. Right? Properties of exponents. And then I can even do one better. This just becomes x, e to the x. So that is my integrating factor. I'm going to go now and multiply the differential equation where I left off by the integrating factor. And maybe some of you are feeling like really swift on your feet. You remember what to do here. Maybe you're skipping this step because you remember that what happens here is that we end up getting, okay, sorry, I need to make sure that I'm not talking at the same time. Okay, I'm just going to pause there for a second. You'll notice that when I did that, I just very swiftly simplified as well. Because when I multiply x e to the x by e to the negative x sine 2x. E to the negative x times e to the x becomes e to the 0, which is just 1. All right. I also simplified in this step right here. But the point of solving in this way, in this manner, is that when you multiply a linear first order diffie-q that's in standard form by I of x, what always happens is that that left-hand side ends up being the derivative of a product. It's the derivative with respect to x of a particular product. And that product is always y times this integrating factor, x e to the x. Okay? And this equals x sine of 2x. That's the whole point of this method. So what I said earlier was, some of you, maybe you remember, maybe you took a really careful look at your notes and this is all coming back to you very quickly. It is absolutely okay to fundamentally skip this step right here and just go from here to here, because this is the result that will always happen. This is the result that will always manifest. Okay? Now, the whole point is to solve the differential equation, right? Solve the diffie-q. And when we're at this step, I can integrate both sides. Left-hand side leaves me with y x e to the x. And now I have to integrate x sine of 2x dx. Okay? Integrating this, everyone, it's going to require, I think it's going to require parts. Is it? Let me see. Or no, we can just do it in our head, can't we? Yeah, let's just do it in our head. It's going to be negative 1/2 cos 2x. Is that right? No, that is completely wrong. That's not even close to being right. Okay, it's going to require parts. The parts are liate. Okay, those of you who were in BC last year, if you see the shortcut of tabular, go ahead and use tabular. I'm going to do it out for everyone else because they likely don't remember tabular. So the choice of u, the choice of dv. Okay, that's your critical decision. U is picked from the integrand based on what kind of function occurs in this triage, so to speak. Logarithmic, inverse trig, algebraic, trigonometric, exponential. Algebraic, A is right here, okay? This sine 2x is trigonometric. A comes before T in this weird alphabet of ours. So U is x, dv is the sine of 2x, okay? du equals dx. V will equal negative 1/2 cos of 2x. We good? All right, that means this entire right-hand side is going to equal negative 1/2. It's uv minus the integral of v du. Okay, I'm going to do this plus, I'm going to pull the 1/2 through because minus a negative, cos 2x. Pardon my slant here. All right, and then at the end of the day, I'm going to get y x e to the x equals negative 1/2 x cosine of 2x plus, is it 1/4 sine 2x? There we go. Right? Good, good, good. And then, I'm going to put the plus c here. Okay. And then at the end of the day, what I want to do is ideally solve for y, then just merely go ahead and do this mess. Woo, boy. All divided by x e to the x. And look at that. We have solved the diffie-q. Okay? All right. That's a little bit of a review on that first method, that first way of solving a differential equation, right? If your diffie-q is linear, degree 1, first order and first degree. Okay, first order and first degree. And let's just make sure we cover all bases. First order pertains to the number of derivatives, if you will, right? It's just the first derivative here. It's not the second derivative. Okay, that's the order. The degree pertains to the highest power that either the dependent variable, y, or the dependent variable's derivative, dy dx, is raised to. All right, so in this case here, you can see that the highest power that either y or dy dx is raised to is a power of 1. All right, wonderful. Okay, let's see. Let's review the next topic here. Let's take a look at exact DEFEQs. Okay, let's review exact DEFEQs. Generally speaking, when you have an exact differential equation, you have a situation wherein the differential equation needs to be in what I've called differential form. I don't know if I ever called this form differential form for you, but and I think I either used this form or I may have used this form. I think I may have done m sub x dx plus n sub y dy equals 0. In fact, that's ringing bells. Yeah, either of these is fine. So I kind of get confused which was which. It's so funny. I work with someone who's in college, and he's doing DEFEQs right now, and we just use that one for his text, but that's neither here nor there. Okay, so exact DEFEQs, they're usually presented in this form, or it's very easy to get it into this form. I'm just going to pull one from one of these. How about that? Let me make sure I pick one that's going to absolutely work out. Let's grab this one over here, shall we? Okay, let's meet you over in some blank space. I'm going to write it down. I'm going to shrink it way down, then I'll bring it back up. Don't worry. Okay, so it says here, it's dy dx equals y squared plus y over x squared plus x. And I just eyeballed this, so hopefully this is exact. I think it is, just my quick eyeball here in real time, so to speak. All right, so let's go over here, okay? So the first thing you're looking at is you see this differential equation. It is clearly not degree 1. So my method from method 1 there, trying to use the simple integrating factor of e to the indefinite integral of p of x dx, that's definitely out. So now the question is, my menu is not that full right now at this point in our journey. We only have these 3 novel methods. Let's see if it's exact. If it's exact, we've got to put it into kind of the differential form here. You want to set it, collect my left-hand side accordingly, and I'd like my right-hand side to be 0. Okay, now if the right-hand side is not 0, that's kind of something we're going to deal with in the near future here. All right, so I'm going to do that. And I have, let's see, x squared plus x dy, okay? And then is it going to be equals y squared plus y dx? Okay, so I'm going to do this, y squared plus y dx plus negative x squared minus x dy. This equals 0. Everyone good? Let me just check my very quick arithmetic and algebra. Yeah, we're good. Okay, let's check if it's exact. So if a DEFEQ is exact, let's make sure we remember if the partial derivative with respect to y of m equals the partial derivative with respect to x of n, then the differential equation is exact. Okay? And if we do this, we have the following. Okay, so d by dy of m, now I think about it, I think this is just not m sub x, it was just m and n, right? Yeah, m and n. Yeah. Okay. d by dy of m equals 2y plus 1. D by dx of n equals negative 2x minus 1. So, all right, so we're going to have to come back to this one because I haven't reviewed yet. So diffeq is not exact. Okay, let's just hold here and let me just pull up an exact one that's definitely going to turn out to be exact. Sorry about that. In my head, I wasn't able to see that far ahead. All right, I'm just going to pull it up. You know what? I'm going to pull it up from I've got my own little thing right here. Here, I'll do this one. How about that one? Okay. I think we may have even used this one in class. I don't remember. Let's see. Did I use this one in class? We'll see. Okay. Here, let's look at this one. 3x squared y, plus y squared dx plus x cubed plus 2xy dy equals 0. Okay. Once again, if you eyeball this, this is not even degree 1, so we're not even going to bother thinking of trying to solve it using the integrating factor of e to the indefinite integral of p of x dx. Let's check. Take d by dy of m, take d by dx of n. And when you do that, I'm just going to pause this and then do it, okay? All right, here we go. So when you check those derivatives, right, they are the same. Therefore, the differential equation is exact. Okay, and here's where the story gets a bit long, if you remember, okay? We have to remember that when you have a differential equation in this total differential notation, the task becomes figuring out what this left-hand side, right, what that left-hand side is the total differential of, right? dz equals this, right? The differential, and I think I may have written it like the differential of z equals this left-hand side of the diffeq. We're going to basically ignore the right-hand side of the diffeq for quite a while. So in the determination of what that function z is, okay, we've got to do a lot of backtracking. This is where I think if you go back here for a second, we talked about what's meant by a total differential. Please look at your notes on that lecture that day, because we did it in class. We talked in great deal about what it means to be a total differential, right? It's the change in the dependent variable by way of the local linear approximation. So in 3-space, the total differential is this, okay? So the task becomes figuring out what function z has a partial derivative with respect to x that is m, and has a partial derivative with respect to y that is n. All right? And maybe you're looking over your notes. Maybe this is kind of just ringing some distant bells here. So the task becomes undoing m. So I'm going to work with m. Okay? So m, we have to remember, is the partial derivative with respect to x of that unknown function z. So we're going to integrate m, and we're going to integrate it with respect to x, okay? And when you integrate this with respect to x, we're going to get x cubed y plus xy squared, plus, we have to remember the constant. The constant in this world, if we're integrating with respect to x, and the integrand has 2 variables, you have to allow for the possibility that your constant could be a function of y, right? Don't lose sight of what this is. This here is that mysterious function z that I want to re-express the entire left-hand side of the diffeq as a differential of, okay? That's z. The thing is, I've got to figure out what this is, okay? So now what I'm going to do is take the partial derivative of z with respect to y, and that should equal n, okay? Because n is the partial derivative of z with respect to y. So let's see. What is dz by dy? dz by dy is equal to, Tyler, I need you to okay, it's all right, plus 2xy plus f prime of y. That is dz by dy. And this needs to equal, where are we? This needs to equal, let me shrink it for a bit, okay? This needs to equal, let's bring it down, this. Let's bring it down. Okay, this has to equal x cubed plus 2xy. Now, you'll see these the left-hand side and the right-hand side are 100% equal. They absolutely match because x cubed, 2xy, 2xy. And yes, the f prime of y matches also because f prime of y just equals 0. Everyone all right? Okay, so if f prime of y equals 0, you good? That means f of y just equals some numerical constant c. So let's walk it back. So what this has told me is I found all the pieces of the puzzle. I now know what z is completely and explicitly. Z is equal to x cubed y plus xy squared plus some numerical constant c. Okay? What that means, now we go back and deal with the entire right-hand side of the equation. I hope this is coming back to you on some level. I hope it's ringing distant bells, maybe very distant bells, but very distant bells is better than ringing on nothing. George, don't say anything cheeky at this point, like there are no bells in my head. Don't say that. I can almost hear you saying that. So this diff EQ now becomes the differential of x cubed y plus xy squared plus c. And that equals, here's where we deal with the right-hand side of the equation, 0. And now we're going to integrate both sides. Integrate both sides. And when you integrate both sides, we get x cubed y plus xy squared plus c equals some other constant k. Okay, and naturally I can amalgamate those two and make this look nicer. X cubed y plus xy squared, I'll just call the constant, I don't know, I'm out of letters, plus q equals 0. Here's my final solution to the differential equation. Okay, all right. Now let's go back to the case when a diff EQ is not exact. So you may remember that if a differential equation is not exact, so now we're on this last point of review here. Whoops. Okay, we're on the last item in our to-do list of review, okay? If you have a diff EQ that is not exact, your first task is to make it exact. And the way you make it exact is you multiply the non-exact diff EQ by an integrating factor. In this case, though, you have two choices of integrating factors. You can have integrating factor 1 or integrating factor 2, okay? And generally speaking, you pick that integrating factor that is easier, okay? Generally speaking, what did I say as a shortcut? I think I said that if m is easier, and m is that which is attached to the differential dx, right? If m is easier, you use the integrating factor. If m is easier, you use the integrating factor. This one? I actually don't remember, but you know what? We'll figure it out along the way. Let's just go do it. I remember this wonderful derivation in class. Well, okay, wonderful for me. I looked out and I saw some rather shell-shocked faces. Shell-shocked but polite faces. But remember I had you derive the other integrating factor for homework? It was really awesome. Okay, let's go over here. So the point here is that when I have a differential equation like this, here's where I left off, right? I check to see if it's exact, and it is not, okay? So I'm going to multiply this diff EQ by an integrating factor. And here, if I look at m and n, they seem almost identically difficult or not. But let's go ahead and just, I'm gonna multiply it by, I want to do this. I'm going to use this integrating factor. E to the indefinite integral m sub y minus n sub x over n dx. And maybe this is the more difficult one, but guess what? We'll figure it out on our own. Okay, here's what you're going to do. Let's make this kind of a tandem exercise. Go ahead and find this integrating factor. Go ahead and multiply it by the integrating factor and see what happens, and then replay me. Okay, yeah, sorry, you got a big fat mess. You can't solve this by making a non-exact into an exact. So sorry, so sorry. This method, this what diffie-q requires what's called a substitution of x equals uv or y equals ux. Sorry, 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 sorry. Okay, let's just, it's okay. All of these are fine. And I went back and I looked at all of this over here. I just noticed that in this section, there's this do not solve. I think because these become very algebraically arduous, but okay. Everyone, we're okay. Everyone's perfectly fine. Don't worry. Everyone just relax. Here, let's do number 14, okay? Let's solve number 14. Let's do number 14, and that's going to, if I eyeball it, let me see. Will that be non-exact? Well, who knows? Let's just go over here and try it, okay? You try it, see if it's not exact or exact. If it's not exact, go ahead and make it exact and replay me. Oh my goodness. Okay, so this is now exact, and you already know how to solve an exact diffie-q. Okay, so right now I'm not able to eyeball very quickly a non-exact diffie-q, but here's the point, okay? So the point of this is that if you have a non-exact differential equation, when you multiply the diffie-q by one of these integrating factors, it turns the non-exact diffie-q into an exact diffie-q, at which point you just proceed through how you solve an exact diffie-q, okay? All right, so what I'm going to do is I'm going to just pick some of these problems for you to do here from amongst this review problem set, and that is what I'd like you to work on, okay? All right, folks, those pink questions, those 4 are for classwork / homework. The next screencast you see on, I think it's Friday, it'll be new content, Bernoulli's method, all right? And I'll also do a screencast of these answers. All right, everyone, thank you for your patience. As an Oscar-winning screencast maker, this was not my most Oscar-worthy. Me. Okay, goodbye.